There's an argument that has been coming up again and again for decades when people claim that the moon landings were fake. Namely, Apollo couldn't have been real because the astronauts would have had to fly through the Van Allen radiation belts, and you can't get through those alive. It sounds dramatic, maybe even logical at first glance, and in this form it's complete nonsense. But as so often, there's a real, highly fascinating core behind the nonsense. Because the Van Allen belts are actually one of the most fascinating phenomena in space travel and a very real problem for modern missions. So today we're going to do exactly what we always do on Mars Chronicles. We take a technical topic, break it down, and look at it objectively. What are the radiation belts really? How do they form? How dangerous are they actually? And where are they strongest? And most importantly, how did Apollo and Artemis get through them without getting fried? My name is Serwan and this is Mars Chronicles. Let's start from the very beginning. What are the Van Allen radiation belts anyway? To understand that, we need two things: Earth's magnetic field and particles from space. The Earth is basically a giant magnet, a dipole with a north and south pole, which creates a magnetic field around the planet. This magnetic field is our natural shield against a constant stream of charged particles coming from the sun, the solar wind. The solar wind consists mainly of electrons, protons, and heavy charged ions. And these particles race through the solar system at hundreds of kilometers per second. When they hit the Earth's magnetic field, something interesting happens. They are not simply stopped, but rather captured. And that's exactly how the Van Allen belts are formed. People often talk about the Van Allen radiation belt, but it's not that simple. In reality, there are two separate torus-shaped main zones around the Earth. The inner Van Allen belt starts roughly at about 1,000 kilometers altitude and extends out to approximately 12,000 kilometers. It consists mainly of high-energy protons and is relatively stable and constant. Its radiation maximum is roughly between 3,000 and 6,000 kilometers altitude. Above that follows a kind of buffer zone, the so-called slot region, an area with significantly lower radiation. With it begins the outer Van Allen belt, which extends from about 13,000 to around 60,000 kilometers. This outer belt consists mainly of high-energy electrons and is significantly more dynamic. It reacts strongly to solar storms and geomagnetic activity. And both zones are not fixed rings, but dynamic, changeable regions that swell, shrink, or shift depending on solar activity. Zones fixed, swell, shift. You can imagine it like two gigantic donuts made of trapped particles floating around the Earth, in a range of about 1,000 kilometers to around 60,000 kilometers in total. For comparison, the International Space Station orbits at about 400 kilometers geostationary satellites at around 36,000 kilometers, and the Moon, by comparison, is on average 384,000 kilometers away. That means any mission leaving Earth's orbit, which flies at 400 kilometers satellites by comparison, there is no magical shortcut. But why are these belts dangerous at all? Because we're not talking about normal cosmic radiation here, but about highly concentrated trapped radiation. Particles with enormous energy. These particles can damage electronics, cause materials to age, and above all, become a health problem for humans. Radiation essentially means energy that penetrates tissue and damages cells there. The risk depends on three things: what type of radiation, how intense it is, and how long you are exposed to it. And exactly. Point 3 is the key to the whole Apollo myth. The Van Allen belts are dangerous, yes, but they're not dementors, and they're not an invisible microwave oven either. And above all, they're not a uniformly deadly force field that instantly kills anyone who flies through them. That's a Hollywood version of physics. Radiation is always a matter of dosage. Here's a simple example. A computed tomography scan in the hospital also gives you a significant dose of radiation. Nevertheless, we survive it without any problems because the exposure is brief. The same principle applies in space. And now it gets interesting. Apollo and Artemis don't just fly straight through the densest parts of the belts. Instead, they use very specific flight paths, certain angles, and above all, very high speeds. That's how you keep the exposure low. And that brings us to the crucial question: how much radiation did the Apollo astronauts actually receive, and was it really deadly? Obviously it wasn't. We've now clarified what the Van Allen belts actually are. Two huge dynamic zones of trapped charged particles that are held together by Earth's magnetic field. And we've established that every mission leaving Earth's orbit has to go through them. There's no secret backdoor out of the solar system, at least not that we're aware of. So let's look at the crucial question now. How did Apollo fly through those radiation belts back then? And what's the plan for Artemis? The standard argument of the skeptics goes something like this. The Van Allen belts are extremely dangerous. Sufficient shielding so humans couldn't have flown through there. That might sound plausible to some people, but there's just one problem. It ignores almost everything we know about radiation and space travel. Apollo didn't just blindly fly through the thickest part of the belts. National Aeronautics and Space Administration very deliberately planned the trajectories so that the inner, proton-rich belt would be crossed as quickly as possible, the outer belt would be passed through in relatively thin regions, and the total time spent in high radiation would be minimized. Apollo launched from a low Earth orbit, performed the so-called translunar injection burn, and then shot toward the moon at high speed. The trajectory led diagonally through the belts, not straight through them. That's a huge difference. An even more important factor is time. Apollo 11, for example, took about 3 to 4 hours to pass through both belts completely, no more than that, and in the really critical areas it was only minutes. Here's a concrete comparison. An astronaut on the International Space Station is exposed to constant cosmic radiation every single day. In contrast, Apollo astronauts were only exposed to the Van Allen belts for a very short time, but a bit more intensely. In the end though, what matters is the total dose. And now let's get to the numbers. National Aeronautics and Space Administration measured the radiation very precisely on all Apollo missions. Every astronaut wore a dosimeter. The measured values range from 0.16 to 1.14 MSV depending on the mission. That's the total dose for both the outbound and return flights combined. For comparison, a typical computed tomography scan of the upper body is about 7 MSV. A transatlantic flight is around 0.05 MSV, and the natural annual dose for a person is about 2 to 3 MSV. That means an Apollo astronaut received about as much radiation on the way to the moon as from a medical scan. So we are very, very far from deadly radiation levels. But wait, why so little? If the belts are supposed to be so dangerous, why were the levels so moderate? This is exactly where physics and mission planning come together, for these 3 reasons. 1. The most dangerous areas are relatively narrow. 2. Apollo flew through extremely fast at over 10 km/s. 3. The spacecraft itself already provided a certain amount of shielding. Aluminum, water, fuel tanks, the structure, all of that doesn't block radiation perfectly, but it's sufficient for short transits. And what about Artemis? Now let's jump to the year 2026. Artemis 2 will basically do exactly the same thing as Apollo. Launch into Earth orbit, translunar injection passing through the belts, and flight to the moon. The geometry is very similar. Artemis will also cross the belts in a few hours. The expected radiation dose is in the same range as with Apollo, maybe a bit higher because we measure a bit more cautiously today. A very quick note on my own behalf. If you like videos like this, long, deeply researched analyses without clickbait or sensational nonsense, then give. There is a very simple way to support this channel directly, the Mars Chronicles channel memberships. The biggest benefit for members is pretty simple. You get to see all the videos as soon as they're finished editing, often days or even weeks before the official release here on YouTube. That means, specifically, no waiting for the release date, but early access. Depending on the tier, you'll also get exclusive behind-the-scenes insights and other extras. And I'll say this openly, it's exactly this kind of support that makes it possible to produce videos of this quality on a regular basis. That's why a huge thank you to everyone who is already a member. You are literally keeping Mars Chronicles running. We're still talking about doses in the range of a few millisieverts, so nothing that poses a serious risk to a healthy crew. An important difference compared to earlier times. Apollo in the 1960s only had relatively few simple radiation sensors. Today the situation is different. Artemis 2 will be equipped with modern dosimeters, real-time radiation measurements, much better models of the belts, and more precise predictions about solar activity. That means today we know much more precisely than back then which regions are safe and when. And with that, let's move on to the next myth. Many people think the Van Allen belts are the biggest radiation problem in space. That's true, but only for Earth orbit missions. Once we seriously consider going to Mars, the situation changes completely. Because the real final boss isn't Van Allen, but galactic cosmic radiation, and especially solar storms. And that's exactly what we need to talk about now. So what happens when the sun freaks out? A strong solar storm can hurl enormous amounts of high-energy particles into space within minutes. If an extremely strong solar storm had occurred during the Apollo missions, it could have actually become dangerous. That was always the real residual risk, not the belts themselves. Apollo mainly had one thing here: luck, but also good planning. They preferred to launch during periods of low solar activity. For short lunar missions, the radiation problem is manageable. But as soon as we talk about longer stays, for example, a gateway station, longer stays on the moon, and especially flights to Mars, then radiation suddenly becomes the central issue. Because outside the Earth's magnetic field, there is no natural shield anymore. And that brings us to the most exciting part of this whole story. How do you protect people from radiation on the way to Mars? What kinds of radiation are there? And why are the Van Allen belts almost harmless in comparison? So far, we've clarified two things. First, the Van Allen belts are real and relevant, but for shorter passages like Apollo or Artemis, they're absolutely manageable. Second, the big myth about the radiation grill is simply physically wrong. But now comes the change in perspective, because the uncomfortable truth is the Van Allen belts are not our biggest radiation problem. They're actually comparatively harmless. The real problem only begins when we completely leave the protection of the Earth's magnetic field. In space, there are basically two types of radiation that are relevant for humans: galactic cosmic radiation and solar particle events. And both are completely different in character, danger, and possibilities for protection. Number one, galactic cosmic radiation constantly comes from all directions of the universe. High-energy particles accelerated by supernovae, black holes, pulsars, and other cosmic sources are extremely energetic and penetrating. And the nasty thing about them is that they're always there, 24 hours a day, 365 days a year, no matter what the sun is doing. Number two, solar storms. These are sudden events where the sun hurls huge amounts of charged particles into space. These are much more intense than galactic cosmic rays, but they're limited in time and relatively well predicted. A major solar storm can massively increase radiation levels within minutes. And that's exactly what would be the most acute risk for a Mars crew. Apollo was only outside the magnetic field for a few days. A flight to Mars takes about 6 to 9 months one way, then a stay on the surface and another 6 to 9 months back. So we're talking about 1 to 3 years in deep space, and at that point, a quick flyby strategy won't help you anymore. But how much radiation are we actually talking about on Mars? Thanks to Perseverance and 2 of National Aeronautics and Space Administration's rovers on the Red Planet, we know that pretty precisely. The radiation dose on a typical Mars flight is about 0.6 to 1 sievert per year. For comparison, an Apollo astronaut only received a few millisieverts. This is a strong simplification, but 0.05 sievert is considered the annual radiological limit. 1 sievert significantly increases the risk of cancer. That means a Mars astronaut would receive more radiation on the way there alone than Apollo astronauts did in their entire lives. On the surface of Mars itself, it's better, but not good. Mars has no global magnetic field and only a very thin atmosphere. The radiation on the surface is about 40 to 50 times higher than on Earth. Better than in open space, but still a serious problem. And how do you protect yourself against it? Now it gets technical. There are 3 basic principles of radiation protection: reduce time, increase distance, and shielding. On a Mars flight, point 1 is almost completely eliminated, so distance and shielding remain as the classic protection methods. Is metal used for shielding? Aluminum, steel, titanium, all of these help against radiation. But when it comes to high-energy cosmic radiation, metal is only effective to a limited extent. In the worst case, thick metal can even create secondary radiation, which makes the problem worse. But it's not hopeless. The best shielding is actually water. And now it gets interesting. The best material against cosmic radiation is something extremely simple. Hydrogen-rich materials such as water, plastic, food, and fuel. That's why there are concepts where water tanks, supplies, and waste are arranged around the crew areas as a natural radiation shield. But there are also ideas for active shielding. For example, we're talking about magnetic shields, plasma fields, and superconducting coils. In principle, an artificial mini-magnetic field. Technically fascinating for a spacecraft, but currently extremely difficult to implement. And the silver elephant in the room, what is SPACEX doing with Starship? Starship has an advantage because of its size. More volume means thicker structures, more fuel. At least on the tank side, the crew has more options to set up protected areas. A Mars Starship could, for example, have a small radiation shelter in the middle, surrounded by tanks and supplies, and Artemis. Here, everything is much simpler. The stays outside the magnetic field are short, and the flights last days, not years. That's why, for lunar missions, conventional shielding, good planning, and real-time monitoring are completely sufficient. A point that is surprisingly rarely discussed. Radiation is not just a medical problem. It's also a huge issue for electronics, computers, sensors, memory chips, and cameras. All of that can be disrupted or destroyed by high-energy particles. Many satellite failures are caused by exactly that. So it's time for a clear, honest conclusion. Question number 1. Are the Van Allen belts an insurmountable obstacle? Short answer, no. Longer answer, absolutely not. The Van Allen belts are dangerous, but above all, they are spatially limited. Their exposure time can be calculated well, and with proper planning, they can be managed. They are not an invisible field of death, but a physical phenomenon that can be understood and planned for. That's exactly what National Aeronautics and Space Administration did back in the 1960s, and that's exactly what Artemis will do again. Question number 2. Did Apollo astronauts really fly through the belts? Yes, and with measurable documented radiation doses that were completely within acceptable limits. Far from being grilled or deadly, and far from what conspiracy theories claim. Question number 3. Is radiation in space still a serious problem? Absolutely, just not where many people suspect it for short lunar missions. The real problem only begins when we spend months traveling in deep space, living permanently outside the Earth's magnetic field, or even spend years on the way to Mars. There, we're talking about completely different doses, risks, and protection concepts. There, we're talking about massive shielding, clever architectures, radiation shelters, good timing in the solar cycle, and maybe entirely new technologies. Here, radiation is one of the biggest unsolved problems in manned space travel. But even that isn't a physical impossibility, it's a technical engineering problem. And finally, perhaps the most important thought, the Van Allen belts are a very good example of how myths arise. A real phenomenon, a real risk, but completely misinterpreted. Many people hear radiation belts and immediately think of Chernobyl and death zones. But in reality, they're more like a busy highway. Dangerous if you run through them without a plan, but totally manageable with the right route, speed, and equipment. By the way, without the Van Allen belts, life on Earth would be a lot less comfortable. They're part of our planetary defense system, so you could say they're not our enemy, but our bouncer. The further we venture into space, the more important radiation protection becomes, not just for astronauts, but also for space stations, moon bases, Mars colonies, and long-term infrastructure. Radiation is one of the major issues of the 21st century in space, right alongside energy, fuel, and life support. The Van Allen belts didn't stop humans from reaching the moon, and they won't stop us from going back there either. It's simply another challenge like gravity, vacuum, or heat, and it's exactly these kinds of challenges that make space travel exciting. So next time you hear someone say that flying to the moon is impossible because of the radiation belts, now you know physics beats myth. Write me in the comments. Before this video, did you also think the Van Allen belts were a real showstopper problem? And what do you find more exciting? Moon missions or the big step towards Mars? My name is Serwin, and this was Mars Chronicles. Thanks for tuning in. Per astra.